Let's talk about LC circuits. We've talked about RL circuits. Let's talk about circuits that have a capacitor and an inductor in it. Now, in order for this to work, of course, I have to have the capacitor previously fully charged. An uncharged capacitor with an inductor in it, once I throw the switch, nothing would happen unless I have some charge on the capacitor. So let's say we have a capacitor that's fully charged, and I close the switch, and let's see what evolves. What's going to happen is the capacitor will slowly discharge, putting current through the circuit and putting current into the inductor. And over time, the current in the inductor will decay and then go through the circuit and then charge the capacitor again. Let's assume we have an ideal situation where there are no Joule losses through the wires, and so this is going to act like essentially a harmonic oscillator, a spring mass system, if you will, in a frictionless system. So let's talk about it this way. My initial condition for the fully charged capacitor, I'm going to have Q on the capacitor is a maximum, Q max. There'll be no current in the circuit, and then I'm going to throw the switch at t equals 0. So at t equals 0, right before I throw the switch, all of the energy in the circuit is in the electric field of the capacitor. But as time goes on, once I throw the switch, it will become energy that goes to the magnetic field of the inductor. So this initial energy is going to be 1/2 times Q squared max over capacitance. Energy in the inductor at t equals 0 will be 0. Now, as the capacitance loses its charge, this value is going to decrease. The value of energy in the inductor is going to increase. So the energy in the magnetic field of the inductor is going to increase until it finally reaches a value 1/2 Li squared. I squared L, if you will, or Li squared. At this point, the capacitor will be fully discharged, and all of the energy will be across the inductor. So this is at some, we'll call it t later for now. We'll figure out what that is. So this is very, very similar, as I said, to the conditions of a mass spring system. I think of potential energy in a stretched, fully stretched spring. I can write that as 1/2 kx squared. That's analogous to the case where I have all of my energy in the capacitor. So it'd be Q max squared over 2c. This all converts to, in the case of the mass spring system, converts to kinetic energy, 1/2 mv squared. For the moving mass on a spring, let's say, this converts to the energy in the magnetic field of the inductor, which is 1/2 Li squared. And this will go on and on indefinitely. So you're going to have energy in the electric field converting energy in the magnetic field, back and forth and back and forth. And if there are no dissipative effects, this will go on forever, essentially. Let's look at it more closely. At any arbitrary time, so these are the extremes, but at any arbitrary time, I can write the energy as Q squared over 2c, where Q is however much charge the capacitor has at that time, plus 1/2 Li squared, where I is whatever current is going through the inductor at that time. Conservation of energy says this is always going to be true. Excuse me. Let's look at how this dissipates. I'm going to take the time derivative of the energy. That has to be 0 because it's constant. Notice what happens though. I'm going to write this as d dt Q squared over 2c plus Li squared over 2, which I can write as Q over c dq dt plus Li di dt. And of course, that has to equal 0. Again, energy is conserved. I would like to have my terms all the same in a differential equation, and to do that, I have to say, well, I know that in this case, I can write I as dq dt, and di dt as second derivative of q with respect to t. So my equation becomes, if I do that, L second derivative of q with respect to t plus q over c is equal to 0. Or if I move some terms around, this is going to look like second derivative of q with respect to t plus q over LC is 0. And this definitely reminds us of the differential equation that goes with the mass spring system that looked like this. Second derivative of x with respect to t is equal to minus k over m times x. Or sometimes we wrote that as minus omega squared times x. In both cases, the general solution is going to look the same. So we can write then the general solution for the mass spring case, you might remember, x is equal to a cosine of omega t plus some phase angle phi. We can do the same thing in the case of the LC circuit, so where I can write q is equal to q max times the cosine of omega t plus phi, where phi is some phase angle. Omega in this case, if I look at my variables, omega is obviously going to be equal to the square root of 1 over LC. The current, if I want to take this a step further, the current I can write as minus dq dt. Why the minus? Because if the current is increasing, the charge is decreasing, and vice versa, because the current and charge are going either to the capacitor or to the inductor. I can write this then as minus omega q max times sine omega t plus phi. And so I should say that's a positive. And that becomes a negative because the derivative of the cosine is the sine. Let's make that clear. So in this case, we can say, suppose I have an LC circuit where I have a 58 millihenry inductor. I have a 17 microfarad capacitor, and I have a initial charge, fully charged capacitor of 180 microcoulombs. Let's find, first of all, let's find omega. And the frequency of oscillation. Let's do that first. I know that omega is equal to 1 over the square root of LC, or square root of 1 over LC, same thing. If I put my numbers in, that will give me an omega of 847 radians per second, which corresponds to a frequency, omega over 2 pi, of 135 cycles per second, or per second, or hertz, if you will. So that gives me a frequency of oscillation of 135 hertz. Suppose I want to find the charge on the capacitor and the current in the circuit at some time, let's say t equals 1 millisecond. So suppose I want to find the charge and the current at t equals 1 millisecond. All I would do is plug in to the charge equation for 1 millisecond, and then plug into the current equation, 1 millisecond, in for t, and then I would find that my charge at 1 millisecond is equal to 119.2 coulombs. My current in the circuit is going to be equal to minus 0.114 amps. And so that's a nice simple example of how LC circuits work. Now we're going to come back to these. They seem like there's not that much to them, but it turns out that one of the most important experiments done in the history of physics concerned LC circuits, and it has to do with the production of electromagnetic waves. And we'll be getting to that later on in the course. But for now, we just understand how LC circuits operate. They're very much like a mass on a spring. I want to do one more wrinkle on this. As you might expect, we've done LR circuits, we've done RC circuits, we've done LC circuits. Why wouldn't we do all three of those circuit components together? And that makes for an interesting application in and of itself, the RLC circuit. That again has a correspondence with mass spring systems, as you'll see. So say take an RLC circuit. I'm going to have a battery. I'm going to have a switch. And it will go like so. With an inductor, a resistor, and a capacitor. So there's my inductor, my resistor, and my capacitor. And I have a switch that's going to go between these 2 points, okay? So it's either connect here or going to connect like so. Okay. Watch what happens. In this case, the total energy isn't constant with time because now I have a resistor that can dissipate the energy. So what I have is I still have a condition where the total energy in the circuit that remains is the sum of the energy in the electric field of the capacitor and the magnetic field of the inductor. So I'm going to write it this way. I'm going to write it as Q over C dQ dt plus Li di dt. Now it's not zero, but is equal to minus I squared R, because this is what's dissipated through the resistor. So it's no longer homogeneous. I can bring this over to the left-hand side, and I'm going to get a differential equation. Again, I look at current as second derivative of charge with respect to time. And so my differential equation is a little bit more complicated. It looks like this. Second derivative of charge with respect to time minus IR plus Q over C is equal to 0. Let me write this again. Plus, let me write it this way. Makes more sense. R dQ dt, let's get all the variables the same, plus Q over C is equal to 0. This equation is analogous to a damped harmonic oscillator. So it's no longer an oscillator that keeps on oscillating with the same amplitude. It's something where we would expect to see the oscillations dampen out over time. And that's exactly what we're going to see in the case of an RLC circuit. So what we equate this to, at least physically, would be my dampened harmonic oscillator that looks like this. And you see the three terms that correspond to one another between my damped harmonic oscillator and my RLC circuit. And once again, what we see over time, instead of motion, what we see in the case of an LC circuit, or RLC circuit, is that my charge in the circuit decreases as a function of time. Now we have a couple of designations here. For example, if R equals 0, of course we just have an LC circuit again. And then we have no damping whatsoever. On the other hand, if R is small, let's say R is a small number, small resistance, don't have much dissipation, this is what we would equate to a light damping situation in the harmonic oscillator. And so what we would find is that I could write my charge at any time as Q max times e to the minus RT over 2L times the cosine of omega subdamping times t. Notice this term here is just my oscillations. This term here, of course, is an exponentially decreasing function, which is telling us that the charge is going to be dampened as a function of time. It's going to decrease over time, and I see this, of course, decrease in the size of my curve over there. We can write omega damping as 1 over LC minus R over 2L squared to the 1/2. The other case, the most extreme case, is if I have R large. So now what we have is the case where we have an overdamped function. I can write RC is equal to square root of 4L over C, which is RC is a critically damped resistance. At that point, when I'm critically damped, I still have oscillations, but if R exceeds RC, our function is now, our oscillations are now overdamped, and of course they won't oscillate at all. It's kind of like having a door on a spring that just slams shut because you've lost your damping factor. Again, when R equals RC, we say that the function is critically damped. So that's just a small wrinkle into RLC circuits. In our next endeavor, when we talk about AC circuits, the RLC circuit will again come to prominence, and we'll do that next time.